Full screen people. Full screen.
Excuse me, Professor Subhashish. Can you hear me? This is
Hello.
We can see the slides, but there seems to be some complaint. I don't know. The voice is not clear. Actually, now it's clear. Okay, okay, fine, fine. So we'll just start in another 2 minutes.
hello, Professor Pankaj.
Yes.
Sir, when Professor Subhashish connects, there's a bit of noise from his side. So could you please convey this message?
Okay, no. So I don't know if he's connected at this moment. Maybe he disconnected. And what slides we can see?
Yes, sir.
Yes, he is.
So his audio had a problem. Yeah, right. So let's see again. No, again there is a noise. Yeah, there is a noise.
Now am I audible?
No, we have noise in the background.
Oh, background. Is it better now? Is it better? Shall I start?
Now we cannot see your slides as well as we cannot hear you.
Now you can see the slide?
Yeah. Now we have now there is no noise. Okay, it's much better.
Shall I begin, Pankaj?
No, okay. So I think now everything is fine. So maybe we can start. So our next speaker is Professor Subhashish Banerjee from IIT Jodhpur. And major theme of his work has been to use a theory of open quantum systems and to understand topics in the area of quantum optics, quantum computing, quantum cryptography, non-Markovian phenomena, quantum thermodynamics, and he has done also work in relativistic quantum mechanics using these tools. and also on foundation of quantum mechanics. So he has worked on a diverse set of topics, and today he's going to tell us about impact of non-Markovian physics on quantum thermodynamics. Okay, Subhashish, you can start.
Okay, thank you, Pankaj, and thank you the organizers of QIQT Kolkata uh, for making this very useful uh, meeting possible. What I want to talk to you about today is basically something which is a very small subset of things which are going on very actively. They're very actively pursued. And they come from principally two different directions. One is uh, basically non-Markovian physics. So I'd like to say how that non-Markovian physics comes in. That I'd like to zoom in a bit on that. And second input that comes in is quantum thermodynamics, which in particular, quantum thermodynamics, even though is a very youthful subject, uh, uh, has already developed a vast literature. And in particular, what I want to talk to you about is a very, very simple model of what is known as a quantum battery. Right? A battery is basically you have a system and a charger, basically. So, uh, the simplest possible realistic model of such a thing that you can envisage, I'll talk to you about. And these things, we found that they can be benchmarked by a very useful foundational quantity which goes by basically quantum speed limit. So this is exactly what I want to talk to you about. So non-Markovian physics, where does it come from? It basically comes from open quantum systems. Open quantum system is a huge subject. So one can actually go on and on and on about it. In fact, non-Markovian also is a huge subject. So before non-Markovian, in fact, you have to talk about Markovian. So I'll kind of skip the Markovian part completely. And when required, we can come back to it and talk about it. The model I've chosen here for presentation purposes is a non-Markovian amplitude damping model. You may be aware of what the amplitude damping model is. Basically, a model which models your spontaneous emission. And this is non-Markovian. There will be some time dependence, etc. in that. And actually, this model goes back to the 1990s. It was developed by Garraway, and very recently, I found that, in fact, this model has its root in something which was discussed way back in the 1950s by K.O. Fredericks in his discussions on mathematical aspects of various models of quantum field theory. So this is a very old model, but if you see the literature, they usually call it the non-Markovian amplitude damping model. Sometimes I call it the Garraway model. And I try to benchmark all these things with quantum speed limit time. Quantum speed limit has become a very useful means of investigation. And there are now various aspects to it. Uh, some of the aspects that we have chosen here are some like the physical properties based measures like relative purity and relative entropy of coherence. And then there is this purely geometric based measures like those based on quantum Fisher information and the Wigner-Yanase information metric. So, like, uh, so I'm going to be extremely brief here. The open systems is basically how you systematically try to understand the dynamics of the system of interest, say, for example, your qubit, by taking into account the effect of its ambient environment. Okay. So that is the idea of open quantum systems, and it's a very old and distinguished history. It was rooted in quantum optics and condensed matter physics, and has diversified into various areas, including that in high energy physics. And many of you will be aware of that it got a huge boost when the experimental developments of Vineland's group, which is this Touche et al. And Mayat et al. Papers here, which are in these slides, and Sergei Herosh's group. So where they did made some, for the first time they could compute this decoherence time scales in different setups, like your, for example, cavity QED effects and things like that. So this brought into forefront the aspect, open quantum system aspects to quantum computation and information. Briefly speaking, so this, your total Hamiltonian would be your system Hamiltonian. The qubit, for example, is your reservoir, ambient reservoir. This could be a bosonic reservoir, it could be a fermionic reservoir, and there's the interaction between the two. So you evolve this, you evolve your system totally using this H. It's a unitary evolution. But since you are only interested in the dynamics of S, you take a partial trace over R, and basically you get the reduced density matrix of the system of interest. And the dynamics of this is called, it's more often than not non-unitary, and this is in many cases can be modeled by an equation of motion which is called a master equation. The simplest form of the master equation being, and also one of the most useful one, being the GKLS form of Gorini, Kosakovsky, Lindblad, Sudarshan master equation, which is of course the semi-group evolution, and which I will not be talking about today. Open systems, depending upon what is the relation of HS with the interaction Hamiltonian, can be broadly classified into the non-demolition type. That is where the system and the interaction commute with each other, and there is decoherence without any dissipation. And the second type, which is the more general class, where there is decoherence along with dissipation. So to the former class, some of the common noisy channels in information theory are the, say for example, phase damping channel. And to the latter class, of course, you have this GKSL form, out of which this, your generalized amplitude damping, or the amplitude damping, or the squeeze generalized amplitude damping channel all belong to. Now, open quantum systems has many scales involved. One would be the natural frequency of the system. The other would be the relaxation time of the system. The other would be the memory time in the system, which would be associated with the upper cutoff frequency of the reservoir, or the time scale associated with the temperature. Now, you see, when we talk about the GKSL kind of master equations, there these time scales are very well separated, and that allows a lot of flexibility in the evolution. So for example, you easily get things like rotating wave approximations and things like that. Of course, even when you have
Excuse me, sir. We are not able to hear you.
video because the host has stopped it.
Yeah, that's right. Okay, now you can share your slides again.
अभी भी नहीं हो रहा.
Also
Because
host.
when I'm saying start video,
Uh-huh.
please ask the host to give me permission.
Host,
to
I
start.
mean, yeah, I mean, can you please give him
Yes,
permission?
sir, we are giving the permission. Yes, sir. Please give us a few minutes.
Okay, sure. Now perhaps you have the permission.
Yes,
yeah. Okay.
Okay.
Sorry, I think there was some issues there.
ठीक है, so this will be good. I will have to innovate.
Yeah.
Now the slide is visible.
No, we can see you, but not your slides.
एक सेकंड शेयर स्क्रीन करता हूँ.
Mhm.
Should I share screen with QIQT's 2023's personal meeting room? Yeah, entire screen. Is my screen now visible?
Yeah. Now your slides are visible, and you are
Okay,
also
so
visible.
I'm sorry, there was this confusion that happened.
Maybe you can
I
go.
will
You
just
can go back. You can go back a bit further. More. I think, Sia, you were here somewhere.
Yeah, so this was the first slide.
Okay, then you can
Basically,
go.
I was talking about open quantum systems. So that is straightforward. Open quantum system is basically effect of the system on the environment. Okay, and it was rooted in quantum optics, and some very useful experiments were done by David Vineland and Sergei Hirosh's group around 25 years back, when they could experimentally get a hold on these decoherence timescales, and that gave a major impetus to the field. And basically, open system is about the dynamics of the system of interest, taking into account the effect of the environment. So you start with the whole bunch and then take a partial trace over what is not required. For example, the degrees of freedom of the reservoir. So effectively, you get the dynamics of the system of interest, which is usually non-unitary and is governed by a kind of a master equation. And depending upon whether this system and the interaction commute with each other or not, you get what is known as a decoherence without dissipation, or decoherence with dissipation, basically. So, to the former class, a very common channel is the phase damping channel, and to the latter class is the amplitude damping channel. And why open systems? Basically, in words, what makes the difference between, say, a Markovian and a non-Markovian evolution is basically that in the former case, the time scales involved in the open systems, for example, the natural frequency of the system, the relaxation time, the reservoir correlation time, these are well separated. Whereas when you have memory and the non-Markovian evolution, this clear-cut separation is kind of reduced. So that makes the dynamics slightly more involved, complex, and therefore somewhat more interesting also. And as I said, I would like to discuss this non-Markovian thing using what is known as a Garaway model. These days in the literature, many times it's called the non-Markovian amplitude damping model also. And it's a very simple model. A very important development in this field was this Hall-Kresser-Lee-Anderson construction, wherein they constructed a time local master equation in such a way such that the generator, if it obeys the natural conditions of hermeticity and trace, can be rewritten in a form which is very similar to that of a GKSL master equation, modulo that these decay rates and the Lagrangians, these gammas and the A's, are usually time dependent. Okay, so this time dependence in these rates makes it different from the GKSL kind of semi-group evolutions. Otherwise, the map can be obtained in a similar fashion, except that you have an additional chronological time ordering operation. So this is basically I was trying to tell you about, and there's this divisibility criteria that if you can break any time from 0 to T2 between the 0 to T1, T1 to T2, and 0 to T2, whereas where this intermediate map is completely positive, then you call this map as completely divisible. Two very popular aspects of identifying memory are the RHP measure and the BLP measure. The RHP measure basically makes use of the Choi-Chemiolsky isomorphism. This psi is some maximally entangled state. So this is the trace norm, and if there's a break in complete positive divisibility, then what happens is this picks up a positive value. So you pick up all these positive values and add them up, and that is the non-Markovian nature. On the other hand, the BLP measure makes use of the distinguishability criteria, which is mathematically equivalent to the trace distance. The trace distance being basically satisfying some very useful properties like invariance under unity transformations and contractions under quantum dynamical semi-groups. So basically, if your distinguishability decreases with time, then you say basically the information is going from the system of interest to the environment and gets lost. But if the distinguishability or the trace distance is non-monotonic, then basically what happens is over a period of time, there are situations when the after decreasing it even starts increasing. Okay, and that is a signature of information coming back from the environment to the system. That's why the term information backflow. Okay, and this was the basic simple idea, and this was used to construct this measure. So d by dt of this trace distance. So if usually, say for example, if this is in this GKSL master equation, then this with increase in time, this d would basically decrease. So this will be always less than 0. But if you are saying evolving this under some kind of a non-Markovian evolution, say generated by the random telegraph noise, or for example the non-Markovian amplitude damping noise, then there will be instances where this d would also increase with time and they will be greater than 0. So you pick up all such instances and sum them up, and that is what the non-Markovian measure of BLP is all about. So then I came up to the Garaway model, which is this two-qubit model, qubit model, two-state model interacting with the harmonic oscillator reservoir via this interaction Hamiltonian. And you can check for yourself that the total number of excitations in this model is a conserved quantity. If you restrict yourself to the scenario where the total number of excitations in the ground and excited states is basically does not exceed 1, then this model can be analytically computed. So you can see all the 4 elements of the density matrix, they're computed, and this the non-trivial aspect is the CT, which is basically depends upon the 2-point reservoir 2-point correlation function. So this model is completely analytically tractable. It has memory in it. And so this f function you can choose phenomenologically. So for example, if you choose it as a Lorentzian spectral density, then this C has this very convenient form, is this. Okay. And this is very convenient because, let me tell you, I won't have time to go through this in detail, but this, because of this cos hyperbolic form and this exponential form, depending on the nature of this D, so if this D is, for example, imaginary, then you can see this cos hyperbolic and sine hyperbolic will become cosine and sines. Okay. In that case, this C function would be basically a damped oscillatory term. Okay. That is a very beautiful and simple signature of memory, basically, as per BLP and things like that. Whereas if this D were to be real in all the places, then you see basically this will continue to remain cos hyperbolic and sine hyperbolic, and this will be basically Markovian. So this is a simple model where you can actually go from Markovian to non-Markovian depending upon the relative parameters that you choose. Basically, you can take out this lambda square out of it, and then you will get square root 1 minus 2 gamma naught by lambda. Depending upon the ratio of gamma naught and lambda, you can decide whether this has this break in the monotonicity of this distinguishability function or not. So that's why it's these kind of functional forms are very useful in the are used in the literature very frequently to exhibit memory basically. So the generator of this Garovay model using the Lee-Kresser form is basically can be written like so. And this, you can see this time dependent decay rates and all these things. So very easy to see when it has this Lindbladian form, and it is very consistent with the Markovian semigroup. And also you can check the divisibility criteria as well as this BLP criteria from this basically. So because of the simple form, these decay rates can be computed explicitly, and you can see that the non-divisibility of the dynamical map and the occurrence of a temporal negative rate are synonymous in this time local mass equation. So see, this simple model, one is able to capture a lot of physics that goes into non-Markovian phenomena. And on top of that, it's also analytically tractable. So this is the same kind of calculations. I wanted to also alert the readers that along with this, these two very popular and easy measures, is also one can actually identify memory even in situations which are CP divisible. Okay, so there are maps like the Ornstein-Uhlenbeck, generalized Ornstein-Uhlenbeck noise, PLN noise, and things like that, which are basically CP divisible, but which do carry memory and cannot be identified by the RHP and BLP measure, but they can be done using some other techniques. But I got out of time because of this glitch, and also it's not central to what I will be telling you, so I'll kind of skip this. One thing which I wanted to say in the beginning only, I have said that we will be benchmarking a lot of these things with quantum speed limit time. So this again not a new phenomena, as you can you'll be aware of. This started almost a decade or so after the first development of quantum mechanics started. So Mandelstam and Tam, they discussed the uncertainty relation between energy and time, and they interpreted this delta t as a time a quantum system needs to evolve from an initial to a final state. After half a century of development, including that of Aharonov and Bohm and others, where they characterized energy time uncertainty relation as a bound on the minimal time of quantum evolution. It was brought out that so Mandelstam, what is it, Margolis and Leviton also produced another bound, which instead of the variance now depended on the expectation value of the Hamiltonian. And the uniform bound, which was considered to be tight, was taken to be the maximizer of these two things. This then, over the last 2 decades, had a huge and a very accelerating development in the sense that it was quickly developed to beyond fixed initial pure states to initial mixed states driven systems, and instead of just our between initial and final orthogonal states to arbitrary states of separation. And it turned out that a crucial development here was the geometric development, where which depended on the Burras angle between the initial and the final states. And this was followed. Just let me skip this slide. I'll come back to this. This is basically, this one. So this was basically this Defner and Lutz approach. They obtained a tight bound on QSL, where basically this in the numerator is the Burras angle. This Burras angle is nothing but the Burras fidelity, and which is basically this rho 0 is the initial state and rho tau is the final driven state. And these are some operator norms. So this is the operator norm, this is the Hilbert trace norm, this is the Hilbert-Smith norm. And given this inequality satisfaction, it turns out that the operator norm of the non-unitary generator. So this this curl L is basically the Lindbladian or the generator of non-unitary transformation. This would be, for example, if you have the master equation, then d rho by dt would be on the, and the right hand side would be this L of rho basically. So this is also how these quantities are computed. You place them here and then they compute the trace norms and do these integrations. So it's quite straightforward to make these calculations. So this is the Burras approach. Now this is the geometric approach. A related geometric approach was that where this speed of information was connected with the quantum Fisher information. A very important approach was made along the same time, almost simultaneously, where instead of this geometric approach, the simple approach of relative purity was made. So this was by these people, Del Campo, Clenio, Hulga. So as you can see, these objects here, these Ks are basically the Krauss operators, which we are all very well familiar with. It's a operationally very fairly easy quantity to use to compute these tau QSLs for open quantum systems. Also, because coherence plays a fairly important role in our discussions, we found it useful to be able to discuss these things directly in terms of the L1 norm of coherence. So a very fairly useful prescription is when we could use this L1 norm of coherence directly into this form, and this was made use of in some calculations. It's useful as a calculation of rules. So now I've talked to you about these speed limits, geometric speed limits, basically the Burras angles, the Fisher information, and the physical speed limits like relative purity. And one more I will talk to you about is basically, okay, there's this geometric speed limit by Wigner-Yanase, which is very similar to this one, Burras fidelity, except that this Burras fidelity is replaced by what is this called the quantum affinity. Now it turns out, it can be shown rigorously, it was shown in this paper here, that for unitary dynamics, the quantum Fisher information metric provides a tightest bound. But if you go into a general non-unitary dynamics like the open system dynamics, then this need not be so. So in that case, the Wigner-Yanase Q information metric could also sometimes provide better bound than that of the quantum Fisher information metric. So that is another thought that goes into these things. So see here, for the same model, Garavay model, we have plot where this is the this is all the scaled versions of these cows. So this is the relative purity measure. This is the Fisher information. This is the Wigner-Yanase. As you can see, the Fisher and Wigner-Yanase are quite similar to each other quantitatively. Another physical property-based measure would be that of QSL by coherence. This was very recent. Arun Pati and his group, they developed this. And this, I found it to be useful because this directly made the connection to coherence. This coherence in particular is the relative coherence entropy of coherence. So basically, it's the minimum time needed for the state to attain a particular coherence, starting from an initial coherence. Okay. So these are technical terms which are basically, again, this MathCal L, these are basically your Lagrangians. They come from the dynamics of your system, of your open system. So that's straightforward to do. But you'll see that this measure helps us to directly plumb into the nature of these things with respect to coherence. And also, if I may just skip this slide for a moment. Again, in recent times, the coherence, one was able to identify coherence into coherent ergotropy and an incoherent ergotropy. Okay, I should have talked about ergotropy first. Okay, so sorry, let me come back to this ergotropy here. Ergotropy makes a connection to quantum thermodynamics, and ergotropy was developed by Alavartine about 20 years back, and it refers to the maximum amount of work that can be extracted from a quantum system through a cyclic unitary transformation of the initial state. So it's fairly useful, easy to compute in the sense that the prescription is given. You do a spectral decomposition of the quantum state and the Hamiltonian, and then order the eigenvalues accordingly. And basically, you find this is the ergotropy. Basically. So this ergotropy, in connection with this coherence thing, is very useful because very recently, the coherent and incoherent contributions of these ergotropies were identified. So the incoherent component is the maximal amount of work that can be extracted without changing the coherence, and the coherent part is the work that is exclusively stored in the coherence. Okay, and these are how they can be computed. So this is the relative entropy of coherence, and this is quantum relative entropy, and then this classical relative entropy. Also, it turns out that for the case of a single qubit, the coherent ergotropy can be connected analytically directly to the purity and the L1 norm of coherence. Okay. Along with these things, when you talk about a battery, you talk about the instantaneous charging power of the battery and also the average power of the battery. Okay. So the QSL for coherence and coherent ergotropy can be brought into a very physically motivating form by directly using this in the in the prescription for tau CSL, we can directly use this expression for relative entropy of coherence. So this is what we make use of, this tau CSL. And here are some plots. So this is basically your instantaneous power, and this is your ergotropy. So this is your charging part, this is the discharging part. This dot here is basically the average power. As you can see, this is the scaled up version of tau CSL, and you can see that the basically the charging and discharging properties are directly connected to the peaks and valleys of this tau CSL. This bold line here is basically the coherent part of the ergotropy. Okay. And in this process, you can see there is this, for example, this discharge of the battery. Then again there is a charge, recharge, then again discharge, then recharge, and so on and so forth. Till it becomes like this. So this from the discharge to recharge and so on and so forth. So this is happening purely, we'll see, because of the non-Markovian nature of the evolution. It's all, of course, done.
Subhashish, I'm sorry to interrupt. Can you conclude in about 5 minutes?
Yes, I'm almost through.
Oh, then thank you.
Yeah, so this is basically because of the non-Markovian nature inherent in the Garaway model for the parameters chosen. Similarly, this is a similar kind of plot for a relative purity measure and coherent ergotropy. Now you see, in this plot, explicitly this is shown, this discharging and charging is shown this for the Markovian sector of the Garaway model. But I told you, in the Garaway model, one can choose the parameters in such a way that it can work in the Markovian model regime as well. Here you can see the power, there is only discharge, there is no recharge. So you see, this makes it very clear. Even this thing, the ergotropy, is only falling, there is no up, going up of the ergotropy. So this, we can see very easily from here that to make this model operate as a quantum battery, that is discharge, charge, and so on and so forth, the non-Markovian nature of the evolution is essential. The same kind of thing is now done for, except that this is benchmarked with Fisher information metric here, and here it is benchmarked with the Wigner-Yanase Q information metric. And we find that the peak and valleys for the physical based measures like this coherent state limit and this is relative purity specify the discharging and charging process being exact for the coherent state measure. Whereas for these geometric measures like this is the Fisher and this is the Wigner-Yanase, they specify the completion of the discharging charging process. So actually it turns out that the geometric and physical properties based measures of QSL time bring out a difference from the perspective of discharging and charging process. And the speed of evolution first decreases and then increases, oscillating around a fixed point. So I come to my conclusions, and it is that I try to discuss a simple model of quantum battery modeled by a single qubit interacting with a non-Markovian amplitude damping channel. And we tried to discuss quantum thermodynamic characteristics such as ergotropy and its components and instantaneous and average power. And we tried to see the connection of these quantities with quantum speed limit times. And the revival in the ergotropy of the system or the recharging of the battery only occurred in the non-Markovian. Of course, this is the tip of the iceberg. There are many models. but these simple things also suggest that a lot of interesting things can be done. Thank you.
Thank you, Professor Banerjee. Unfortunately, we had a prolonged network interruption. Still, you managed to conclude in time. So sorry about that. So we can still have some quick questions, okay, about this very interesting topic, of quantum battery. So please feel free to unmute yourself and ask a question.
So I have a question, sir.
Sure, go ahead.
Sir, thanks for the talk. Sir, the power from this quantum battery, how can we use it? Like the battery is getting we are recharging and it's getting discharged. So is it the power going to the environment that it is connected?
Yeah. So it is basically, see, you can think of your battery as your qubit and the charging system as the environment. Okay. Now, if it is basically in the Markovian limit only, then basically it gets discharged and nothing comes back to it. So there is no, but if there is it's in the Markovian, non-Markovian limit, then there's just like that information backflow is happening, right? Simple model.
Yes,
so
yes.
it gets processed and then it comes back and charges. But you will see that the overall envelope also is kind of, it's not as if it goes back to the same level, right? You can see, because this process where dissipation is also there. So like your usual battery also, right? If you use it, after some time it gets depleted, right? Then you have to either recharge the battery or you have to throw it away after some time, isn't it?
Yes. Okay. So this qubit, since the environment backflow, that information backflow is making like recharging the battery kind of.
Yes. It's like a dynamical recharging, basically.
Okay. Okay, sir. So I need to connect one, to use the power from the battery, battery is quantum battery. I need to connect some other system, right, to use that power somewhere.
No, so here we are kind of relying on the environment in a very big kind of hello.
Yeah, hello. Yes, go ahead.
Yeah, so here the environment is like a very huge, like a power, what do you say, power storage device or something like that.
Okay. So
But there are limits to everything, basically.
So we can have at most one more question because of this interruption we had. So we are, we are a bit late. So please, so one more question if anybody has it. Please feel free. Okay.